Today I'd like to look at integrating powers of tangent. And remember, we do know already how to handle the first couple of powers. So tangent to the first, we looked at this in Calc 1. It's a U substitution because tangent's sine over cosine, right? And typically, we wrote it as negative the natural log absolute value of cosine, which is how it arises when you do the U substitution. Typically, this is one we just have memorized after Calc 1. And the thing I don't like about this is in all of our derivatives and integrals and identities, tangent and secant tend to go together. So we can write this, though, if we bring that -1, remember your rules of logs, that's the same as natural log absolute value of cosine to the -1, which is secant. So an equivalent way of writing this, and a way that makes it easier for me to remember, is to write it as natural log absolute value of secant. So that's the way I'm going to write it. There's nothing wrong with using that way. That's fine. And if you ever forget, you can always rederive this by U substitution. Just rewrite tangent as sine over cosine. So we already know first degree from Calc 1. Second degree is going to be the basis of how we do all degrees. Now, none of our trig functions in Calc 1 had the derivative tangent squared. The derivative of tangent, if you remember, was secant squared. Derivative of secant was secant tangent. So neither of those work. But using the Pythagorean identity here, tangent squared plus 1 is secant squared. So tangent squared is secant squared minus 1. Now the nice thing about that is that's one of our derivatives from Calc 1. The derivative of tangent is secant squared. So once we use the identity, we can now integrate that. And we end up with tangent x minus x plus a constant. All right. Any degree higher than second degree, and it doesn't matter whether it's even or odd, so there's not a special technique for evens or odds here. They're all done the same. They all reduce the degree down 2 at a time using this identity. So if you start with an 8th degree, we'll knock it down to a 6th, then a 4th, then a 2nd, and when you get to a 2nd, you get to here. The only difference between even and odd is if you start odd, you're eventually going to end up with this integral. So that technique, that's called a power reduction technique. So let's just look at tangent cubed. We'll reduce that down to tangent to the first. And if you understand that process, all other higher degrees will use that same process over and over again. So let's look at tangent cubed. So no matter what the degree is, the idea is you'd like to use the Pythagorean identity. So you want a tangent squared. So it involves, the first step is always factor off tangent squared. Now apply the identity. Tangent squared is secant squared minus 1. And you almost have a U sub at this point. U is tangent, du is secant squared, but that minus 1 is a problem. So I'm going to break it up into 2 integrals. So I'm going to distribute the tangent x to both those terms. So you have tangent x times secant squared. That's one of my integrals. And then tangent x times -1, so minus the integral of tangent. Now, this works by U sub, and this is now first degree, which we know how to do first degree. And that's really our power reduction. We reduced a third-degree tangent down to a first-degree tangent, and then this other integral will always work by u substitution. So u is tangent, du is secant squared x dx. So we have the integral of u du minus, and I'm going to use my form there, natural log absolute value of secant x. And then finally, that's just 1/2 u squared, and u is tangent, so it's 1/2 tangent squared minus natural log absolute value of secant. And now that all the integration is done, I need my plus c there of integration. Okay, so let's see, what would change for higher degree? So I said that the process is a power reduction. You reduce by 2 degrees each time by using this identity. If this had been tangent to the 30th degree, you factor off 2, this is now 29th degree, right? That's 29th degree now, that's 29th degree, and that's 29th degree. Excuse me, if that's 30th, take off 2, that's 28, 28, 28, 28. So you reduce by 2 degrees because you factored off 2. It really doesn't matter that this one's 28th degree because the u sub still works. It would just be u to the 28th. So this little part doesn't get any more difficult. It's always going to be a u sub. The degree might change here if this is higher. But all you accomplish on this integral is lowering by 2 degrees. So if it started off as 30th degree, this is going to be 28th. Go through again to get it to 26th, then 24th, and keep going 2 at a time. So the higher this goes, the more times you have to repeat this process to knock it down 2 degrees at a time. So the important thing to know then is that there is an antiderivative. No matter what degree tangent is, you can reduce it 2 degrees at a time. And if the original thing's odd, you'll eventually end up at tangent to the first. And if the original thing is even, you'll eventually end up at tangent squared. Either way, you'll eventually end up at the antiderivative. So there will be an antiderivative. So regardless of degree, factor off a tangent squared, use the identity, break it up, distribute and break it up. This will work by u sub, and this will be 2 degrees less than what you started with. Now just repeat as needed, regardless of even or odd. Next time we'll look at powers of secant, which in that case it is going to make a difference whether the degree is even or odd.